Today we explore one of physics' most fascinating mysteries, the entropy reversal paradox. Can disorder actually decrease spontaneously? Entropy measures disorder in systems. The second law of thermodynamics tells us it always increases, but recent discoveries challenge this fundamental principle. Let's start with the cornerstone of thermodynamics, the second law. The second law states that the change in entropy delta S is always greater than or equal to zero for isolated systems. This means in any spontaneous process, the total entropy of an isolated system must increase or stay constant. A classic example: gas molecules starting in one corner of a room will spontaneously spread out to fill the entire space. Order transforms into disorder. But what exactly is entropy? It quantifies the number of possible microscopic arrangements that produce the same macroscopic state. Boltzmann's famous equation, entropy S equals Boltzmann's constant times the natural logarithm of W, the number of microstates. Boltzmann's constant is approximately 1.38 times 10 to the negative 23 joules per Kelvin. Now here's where things get interesting. Scientists have observed something shocking in small systems. Here's a crucial question. Can entropy spontaneously decrease in real physical systems? The classical answer from thermodynamics is a firm no. The second law forbids it. But modern experiments reveal yes, it can happen in sufficiently small systems. In systems with just a few particles, thermal fluctuations can temporarily reverse entropy. The system becomes more ordered for brief moments. The key to understanding this paradox lies in the fluctuation theorem. The fluctuation theorem states the probability ratio. The probability of negative entropy production over positive entropy production equals e to the negative a over kb. This means, while entropy can decrease, the probability is exponentially small and depends on the magnitude of the decrease. Let's consider a concrete example, a tiny colloidal particle suspended in water. Water molecules constantly bombard the colloidal particle from all directions. Usually this increases entropy, but occasionally fluctuations can briefly decrease it. Let's calculate the actual probability of observing negative entropy production. Suppose we want an entropy decrease of 10 times Boltzmann's constant. The probability would be e to the negative 10. That's approximately 0.000454, or about 4.5 times 10 to the negative 5. This means only about 1 in 22,000 events would show this entropy reversal. Rare, but not impossible. Visualizing 100 events, we'd see 99.995% following normal entropy increase, but a tiny fraction showing reversal. How long must we wait to observe these entropy reversals? This raises an important question. How long must we observe a system to witness entropy reversal? The answer depends critically on the system size and temperature. The typical timescale tau is proportional to e to the delta S over kb. For macroscopic systems like a cup of coffee, this timescale is astronomical. We'd wait longer than the age of the universe. The timescale increases exponentially with system size. Nanosystems show reversals in microseconds, but macroscopic systems would take eons. But for true nanosystems with just a few particles, we can observe reversals within microseconds to milliseconds. These predictions aren't just theory, they've been verified experimentally. In 2002, Wang and colleagues directly observed negative entropy production in colloidal particles. They used optical tweezers to trap and monitor single colloidal particles in water. Their measurements showed entropy mostly increasing, but with occasional dips below zero, exactly as the fluctuation theorem predicted. The experimental results matched theoretical predictions with stunning accuracy. Now for the critical question, does this violate the second law of thermodynamics? Does observing spontaneous entropy decrease mean the second law is wrong? No! The second law remains valid. This phenomenon actually refines our understanding. The key is the average. The expectation value of delta S is still greater than or equal to zero. The second law is fundamentally statistical. It describes average behavior, not every single event. Even with fluctuations going down occasionally, the overall average trend is always upward. The second law describes this average. There's a deep connection between entropy reversal and information theory. Changes in entropy relate to changes in information. Delta S equals negative KB times delta 1. When we gain information about a system's microstate, we effectively reduce its entropy from our perspective. This relates to Maxwell's famous demon thought experiment. Maxwell imagined a demon sorting fast and slow molecules, seeming to violate the second law. But the demon must erase information, which increases entropy elsewhere. Landauer's principle tells us that erasing one bit of information requires at least kBT ln2 energy. The minimum energy is Kb times temperature times natural log of 2. Understanding entropy fluctuations has real practical applications. Molecular motors in biological systems exploit thermal fluctuations to do work. ATP synthase, the cellular powerhouse, uses Brownian motion and entropy fluctuations to synthesize ATP molecules. Engineers are designing nanoscale heat engines that harness entropy fluctuations. In quantum computing, understanding entropy fluctuations helps design better error correction protocols. This field has given birth to stochastic thermodynamics, a new branch of physics. Total entropy change equals system entropy change plus bath entropy change. Stochastic thermodynamics applies thermodynamic laws at the trajectory level, not just ensemble averages. Different individual trajectories show different entropy behaviors, but the ensemble average still obeys the second law. Entropy production sigma equals the average entropy change minus the minimum entropy change. Let's tie everything together and resolve the apparent paradox. The second law of thermodynamics applies to ensemble averages over many events, not individual realizations. Individual trajectories can temporarily violate the second law through thermal fluctuations. The probability of violation decreases exponentially with the size of the entropy decrease. Think of it like a whirlpool. Most motion goes in one direction, but occasional eddies flow backward. The net flow is still toward higher entropy. This discovery has profound philosophical implications for our understanding of nature. Even classical thermodynamic laws are fundamentally probabilistic at their core, not deterministic absolutes. Order can emerge spontaneously from disorder in small systems through thermal fluctuations. This raises a fascinating question. Does this help explain the thermodynamic arrow of time? The arrow of time emerges from statistical asymmetry. Forward in time means toward more probable states. Most trajectories point toward higher entropy, defining the forward direction of time. Rare reversals don't change this fundamental arrow. Let's do a concrete calculation for a familiar system, a cup of coffee. Consider a cup of hot coffee at 90 degrees Celsius containing 200 milliliters. This contains approximately 10 to the 25th power molecules. What's the probability that this coffee spontaneously heats up by even 1 degree? The entropy change would be approximately 10 to the 20th times Boltzmann's constant. The probability would be e to the negative 10 to the 20th power. This number is so incomprehensibly small that it might as well be zero for all practical purposes. For macroscopic systems like coffee, entropy reversal is effectively impossible. You'll never see your coffee spontaneously heat up. Now let's contrast this with a truly microscopic system. Consider a single molecule held in an optical trap. Here, n equals 1, just one molecule. An observable entropy reversal might involve delta S of about 10 kb. The probability is e to the negative 10, approximately 0.000045. This is observable. If we watch for a few seconds to minutes, we'll see entropy reversals. For single molecules, thermal fluctuations are significant compared to the system's energy. Entropy reversals become routine observations. Where exactly is the boundary between classical and quantum fluctuation-dominated behavior? How small must a system be for entropy reversals to become observable? The critical number is roughly 10 to the 6th to 10 to the 9th particles. This corresponds to nanometer to micrometer length scales. The frequency of entropy reversals drops dramatically as we move from nanoscale to microscale to macroscale systems. Let's summarize this fascinating journey through the entropy reversal paradox. First, entropy can indeed spontaneously decrease in sufficiently small systems through thermal fluctuations. Second, The probability of such reversals decreases exponentially with system size. Third, the second law of thermodynamics remains valid when properly understood as a statistical law. Fourth, the fluctuation theorem precisely quantifies when and how often reversals occur. Fifth, this discovery opened entirely new fields like stochastic thermodynamics. The entropy reversal paradox reveals nature's exquisite balance. Rigid laws emerge from probabilistic foundations, and rare fluctuations don't destroy universal trends. The paradox doesn't violate the second law, but instead enriches our understanding of it. It reveals that thermodynamics has a fundamentally probabilistic foundation, even in classical physics.